let me start by pointing out when I go to OneNote, it does not show any empty lectures here. Do you guys see empty lectures showing up in the list?
It says like Untitled when you go onto it.
Yeah, I don't know why, but as you can see, I have it set up right. It bugs me when things look wrong. We had the exam yesterday. It was not as rosy as I would hope. There were two people with very high scores, and then the third highest score was in the mid-70s. And I hope that with the regrading of the last three problems, that scores will look better. We have a little bit of complication. One person hasn't taken the test yet, so I can't give you back your test to look and say, do you want those to be graded yet at this point? But I will, as soon as we have the last person take the test, and then we'll figure out where to go from there, because it's not good to have the test average was, I think, 67% just by the multiple choice, and you want it to be 10% higher than that. You want the average to be in the high 70s, not in the high 60s. So I'm hoping that with regrading it will come up to something that is much more representative. And I saw a lot of people who I know worked very hard and were good students who didn't have the scores that I expected. So I will be working with you to try to figure out how to best make sense of these scores. So any questions about the test at this point? Okay, now I already talked, in your reading quiz, it was about angular momentum. Well, I already talked about angular momentum. We had James come up here and spin around holding the the wheel. And so I thought maybe I should go back and talk a little about simple machines. After all, the lab next week is going to be on simple machines. Cover simple machines, and then I will have a homework assignment that's on simple machines that will be due Monday after break. Everybody on board with that? All right, let's go. Well, first, before I do that, equilibrium problems. I have like 3 problems I forgot. Then the simple machines. Problems just to help us, once again, get into the groove of how to solve these equilibrium problems. So this problem, I know it's kind of small type. A uniform stationary ladder of length L and mass M leans against a smooth vertical wall while its bottom legs rest on a rough horizontal floor. The coefficient of static friction between the floor and the ladder is mu. Notice it's static. This is an equilibrium problem. The ladder is hopefully not going to be sliding away from us. We don't like to climb ladders that are sliding away from us. The ladder makes an angle of theta with respect to the floor. A painter of weight 1/2 m, that's just to make life easy for us. We only have 1 m to worry about. The ladder's total m, the painter's 1/2 m. Stands on the ladder distance d from the base. That doesn't have a question yet. That's just laying out the situation. This picture then illustrates the situation. You have the total mass of the ladder m. I'm going to draw forces here before I even read the questions. What forces? Well, we should even be more specific. What is the object that I'm interested in for this problem? I haven't even read any question things, but what is the object I'm going to be interested in?
The ladder.
It's going to be the ladder, right? The ladder is the thing that was being described. So I'm going to show all of the forces acting on the ladder. And note this is not technically a free body diagram. I'm showing the forces where they're acting. So let's start naming off the forces acting on the ladder. Okay, force of gravity. Where does the force of gravity act? Okay, its direction is down. Its location? Okay, where the center of gravity is, and it says uniform ladder. Uniform is a code word to tell you its center of mass is at its geometric center, which would be halfway up the length of the ladder. So I have the force of gravity acting on the ladder, which is mass times G. Okay, there's one force. What's the next force? Okay, normal force from the floor. There's also one at the top. So I'm going to call this force normal. I'm going to call this one here force wall. They're both normal forces, but I have to give them different names. I can't call them both force normal. I could call them force normal 1 and force normal 2. It'd work.
So is that the correct way to put it, straight up and straight?
Because normal means that.
Yeah, but I just meant like, so we're just assuming that they touch flat on at that point? Because like obviously if you look at the picture, it's slightly.
It would not matter because the normal force is always coming directly out of the surface in the normal direction. It's a good question.
Yeah, it would go into dimensions.
Other forces. There are 2 more.
Is that including the gravity from the person?
Okay, that's one of the 2, and that's the other of the 2. We have the force of gravity on the person, which is equal to their mass was 1/2 m times g. And then we have the force of friction. Now, a lot of people got this one wrong on the test. What direction is static friction pointing?
Oh, wait, in the spring?
Yeah. What direction is static friction always going to point?
Opposite to where you're stretching?
It's going to point in the direction necessary to keep it from sliding. So if there was no friction, what would the ladder do? It would slide out. So what direction is the force static friction going to have to point? Toward the wall. And it's less than or equal to mu s force normal. In the test problem, you had the mass was pulled down the slope because it was stretching the spring. What direction would the mass move if there was no friction? It would go back up the slope. So what direction did the friction have to point? Down the slope. So we have all of our forces drawn. Now I'm going to read the questions to go with this. So question number 1, find an expression for the magnitude of the normal force exerted by the floor and the ladder. Number 2, find an expression for the magnitude of the normal force exerted by the wall. 3, find an expression for the largest value of D for which the ladder does not slip. And then finally, put some numbers in. So we're finding a bunch of expressions. We're starting with finding the value of the force normal that I have marked Fn. So if you look at this problem, first thing, well, what's the first thing you think you would do? Like, let's say you had no idea where to go with this. What would you do if you had no idea? I go out the door. Hopefully you go back to what we did when we worked these kinds of problems in lab a few weeks ago. We need to define component directions, which is done for us already. And then we need to break it into components. So I'm going to make X and Y directions. And so for each force, okay, there I've got all of the forces listed. Hopefully I left myself enough space to put in values. And because force normal is in the y direction, I'm going to do my y's first. So I'm going to do my y's, and I will have the force of the wall in the y direction. Well, the force of the wall in the y direction is horizontal, so it's 0, right. Force of gravity in the y direction from the person, it's down, so what does that make it? Force of static friction in the y direction, it's in the x direction, so that's 0. Force gravity ladder, I forgot one more force, the one we're looking for. So what's force of gravity of the ladder in the y direction? It's what?
It's negative.
Okay, it's negative, and its value is mg. And then force normal in the y direction. It's positive, and it's all of it. So now that I have all of those forces, sum of the force in the y direction is mass times acceleration in the y direction. If the ladder is stationary, what's the acceleration in the y direction? 0. So in this case, I'm just adding up the column. Force normal minus 1/2 mg minus mg equals 0. So force normal is equal to 3/2 mg. Yeah, nice box. Okay, that was fairly easy. That's the answer to the first one. I did the y direction because that's the direction of the force I was looking for. Question?
So why is it 1/2 mg instead of just mg?
Because it says the mass of the person is 1/2 m.
Oh, okay.
Yeah, that was the mass of the person.
Oh, okay, sorry.
Anybody notice a mistake in the problem's wording? A painter of weight 1/2 m. That's his mass. Not his weight. Okay. Got that fixed. So we have the answer for the first one. We found an expression for the magnitude of the normal force. Now an expression for the normal force, the wall. I only have 2 horizontal forces, right? If I go through this, I'll leave it in red here. If I do the horizontals, the wall in the x direction is minus force wall. Gravities are 0. Normal is 0. And this one here, I just have less than mu s times force normal. I don't have a possible answer for the force of the wall because my force of static friction, I only know it's got to be less than mu s times force normal. And the problem did say that it wants an expression for the magnitude of the normal force the wall exerts on the ladder, not what's the maximum it could exert. So I'm going to have to do something more. This here is stuff that was covered on the exam we just had. What's the new thing that I'm going to add? Torque. So I'm going to add the torque, and again, the torque is technically in the z direction. And so the torque from the wall, the torque from the person, the torque from static friction, the torque from gravity in the ladder, that was gravity in the person, and the torque from normal. Now, when you do the sum of the torques, you have to choose a location to sum the torques about. And choosing the right location can make life easier. So if we look at our picture, I want to find force of the wall. So I cannot choose to sum my torques about anywhere on this line and find the force of the wall. Why would anywhere on that line fail? Because the torque caused by the force of the wall would be 0. So I can't choose. Why is it 0? Because the force of the wall is pointing parallel to the line, or is on the line I just drew. Yes, Trace?
I'm just wondering why the force of the wall in the x direction is not negative.
It is. I replaced the negative and put an equal. I had a negative there. I thought it was sloppy. I erased it, and yes, my brain went sideways. Thank you for correcting that. Okay, so the question then becomes, where should I sum the torques? What would be the easiest place to sum the torques? There's one answer that's easier than the others. Well, there are 3 answers that are easier, but one that I think is easiest. Good?
The static friction.
No, what location?
Oh.
In the center of gravity.
Okay, the center of gravity would make the force of gravity on the ladder make 0 torque.
What do you mean the base?
It would remove 1. If we choose the base, that would remove 2 forces. So that's what I consider to be the easiest place because it removes 2 forces. So I'm going to sum the torques about the base because it's all about the base. Sum the torques about base. That is perfectly written about. Everyone could read that. And so now the torque of the wall. Now remember the equation for torque, it's R cross F, which means that the magnitude of the torque is equal to RF times sine of the angle between the two. Cross product multiplying the perpendicular parts. And so sine theta, if theta is the angle between the two vectors, then that will give me the perpendicular parts. So if I look at the wall, the R vector for the wall is going from, okay, that doesn't stand out very well. I will use a highlighter. It's going from there to there. That's my R vector. It has a direction to it. It's going like that. And of course, the force, well, that was beautiful. The force is going like that, so I need the angle between R and the force. How would I find the angle between R and the force? Or you could just find the perpendicular distance if that's easier for you. What is the perpendicular distance to the force wall from the base? What direction is force of the wall? Quick answer.
What?
Horizontal, okay, to the left. So what direction is perpendicular to horizontal? Vertical. So what's the vertical distance from the base of the ladder to that horizontal force wall? We have a triangle here with length L as the hypotenuse.
Do we know theta?
It's what?
Do we know theta?
Theta, we want our answer in terms of theta.
Okay.
So because that's the opposite side, it will be indeed sine theta. So it's going to be L force wall sine theta. Okay, then we have gravity for the person. Gravity for the person. Come on, erase that bad boy. There we go. Gravity for the person is acting at a distance d. It's a vertical line now for the force. So if it's a vertical line, I want the horizontal distance from the base of the ladder to where the person is. So if I have a hypotenuse of d, and I want to find the horizontal part, which trigonometric function will tell me that perpendicular component? I have a triangle. Nobody's talking here, so I'm drawing the triangle. I want the perpendicular part, which is this distance right here. What part of the triangle is that? It's the adjacent side. So the trigonometric function that relates hypotenuse D with the adjacent side, cosine. And then static friction, that's 0 because the force of static friction goes right through the point I'm summing the torques. Gravity of the ladder. Gravity of the ladder is a distance L over 2 from the base because it's at the center of mass. Has a force of mg. And once again, that's the horizontal distance, so I have cosine theta. And finally, torque from normal. What's the torque from the normal force about the base? 0. It wouldn't make it rotate about the base.
What does that L mean again, the one up there? And where the torque of the wall?
L was defined as the length. Let me erase this. There's L.
Oh.
It was the length of the ladder.
Okay.
So now, for torque, you do sum of the torques equals I alpha equals 0 because it's not changing its rotational rate, staying constant at 0. So read these down and I have, I didn't pay attention to the directions. Torques, you have to pay attention to directions using the right-hand rule. Let's do this quickly. What direction is the torque due to the wall?
Counterclockwise.
Okay, counterclockwise. That's correct. That force would make it rotate counterclockwise. Counterclockwise is positive. The other way to calculate it is with the right-hand rule. Index finger in the direction of the R vector. Orient your hands, your middle finger's pointing in the force direction. Thumb comes out positive. So the torque to the wall is positive. What about the torque due to the person standing on the ladder? What direction would that make it rotate?
Clockwise.
Clockwise, which is negative. Or you could have done R again, same as before, but then I need to orient my hand so I can point my finger in the direction of that force. Thumb points in, negative. So that was negative. And what about the torque due to the ladder? Exactly the same geometry, so that's negative as well. So there I have it. That's my sum of the torques equation. Now I'm looking for force wall. So I'll move the things that aren't force wall containing to the other side of the equal sign. L times, well, that's not an F. Okay, I factored out everything I could, which was mg cosine theta over 2, and I was left with just d plus L. So solve for FW. L over L is 1. So when I divide it by L, I just put it in like that. So the L over L gave me 1. And so there's an equation. Couldn't read that D very well. There's an equation for the force of the wall as a function of our variables, including D, how far the person has walked up the ladder. Now, so far this problem has been a straightforward application of the conditions of equilibrium. And justice for all, I suppose. Equilibrium. But now for the last part. Find an expression for the largest value of D max for which the ladder does not slip. Okay, now, oftentimes no one ever even realizes that if they step on the base of the ladder, step on the bottom rung and it doesn't slide, that doesn't mean it's safe to climb to the top. We tend to assume if you can start the ladder, you can climb to the top. That's not true necessarily. As you climb up the ladder, about that base, you're creating more and more torque to try to make it rotate, which requires the force of the wall to increase greater and greater. But if the force of the wall becomes bigger than the maximum static friction force that it can support, it's going to accelerate away from the wall. So you have a situation where you could climb halfway up a ladder and you think you're great, and then you go up 2 more rungs and you find yourself chin down on the floor. Nobody wants that to happen. This is a good time to bring up ladder safety. In the fire department, we had to do a lot of stuff with ladders. One of the things they taught us was, of course, you never climb a ladder unless there's somebody footing the ladder. Footing the ladder is somebody standing at the bottom. You can either foot it from the front where they're standing like this and their feet are at the feet, hold in place. Or you can foot it from the backside and you're pulling back. But if you have to climb a ladder with somebody not footing it, or even if you're setting up the ladder and somebody's going to foot it, basically stand straight up, hold your hands out, and if your hands are on the sides of the runners, that's about the right angle for climbing the ladder. So if you're setting up a ladder and you're wondering, how steep should I make it? That's how you judge it. Ladder safety, why? Because physics. If it's too straight up, what's going to happen? Yeah, your weight is going to be back behind the feet. If your weight is back behind the feet, you're not in equilibrium and it falls over. If your weight's in front of the feet, then you're good. And so that's why you have that judgment thing, so that when you step up on the ladder, you're still going to be vertical, assumedly, which makes your weight in front of the feet. If you have it too steep like this, you know it's going to slide out. Okay, so back to this fine expression for the largest value of D max. Looking at what we've done, you might just look at my table and say, wow, he's explored all but one option, right? I did the sum of the forces in the y direction. I did the sum of the torques. I didn't do the x. It's a good sign that might be where I'm going. It is where I'm going. Why am I going to the x? Because the force of static friction is in the x direction. It asked us a limiting case. What's the maximum distance a person can go up? When it says maximum, then I'm all, oh, so that's going to be when the force of static friction is at its maximum. So once again, there's like clues, dog whistles if you want to use the political term these days, to tell you, oh, that means that we are going to change this from a less than or equal to an equal for part C. Changing it because of the word, well, it says largest here, or D max. So in that case, I want to not slide. So my acceleration in the x direction is still going to be 0 if it doesn't slide. Once it slides, it's not 0. Once again, limiting case. And then reading down, I have mu s force normal minus force wall equals 0. And so I found the force normal, put that in there. I found the force wall, put that in there. And I have mu s times mg over 2 tangent theta. I never use cotangent, I just use tangent, okay? So that's mu s times force, oh crud. That's mu s times force wall, which would be incorrect. Mu s times force normal, which is 3/2 mg minus force wall equals 0. Notice the mass of the person climbing is not going to matter. I'll cancel the masses in both terms. I want to solve this for D, so the first thing I'm going to do is move this across and multiply everything by 2. So I'll have 3 mu s g. Oh, I can cancel the g's too. Let's get rid of those. 3 mu s is equal to 1 over, I cancel the halves, 1 over tangent theta of d over L plus 1. So obviously multiply both sides by tangent theta. Subtract 1 from both sides. And then finally multiply both sides by L. And we have D is equal to L times 3 mu s tangent theta minus 1. I presume I made no mistakes. Keep in mind, all of us are fallible. All of us will occasionally make mistakes. On the test, sadly on those last 3, if you didn't write out your work, a mistake makes a lot of difference in points. So I will go through, and anyone who missed more than 2 of the last 3, that's 2 or 3 of the last 3, I will automatically grade your last 3, even if you don't request it. If you only miss 1 of the last 3, I will leave it to you to request it when I actually give you back the test and you can see. Okay. That is a problem that has gone on tests in the past. It's got 3 different summations I had to do, one more than before. In terms of the actual difficulty, it's not super difficult, but there's the complexity of remembering all of the different steps. So does anyone have questions about that solution? Leslie?
How did you know specifically that you're going to look for that little triangle there where the distance D is?
Whenever you're finding torque, torque is R cross F, or the perpendicular distance from the point you're summing about to where the force acts, multiplied by the force. And so I was looking for the perpendicular distance. So the vertical on that triangle was where the force was acting. And so the perpendicular distance was the horizontal in that triangle, because horizontal is perpendicular to vertical.
So the vertical force was the force of the force gravity of the ladder right there where the person is?
Right, that was the force gravity from the person.
Okay, and then you know that it's going to be horizontal.
Because the force was vertical, that means the perpendicular distance is going to be the horizontal distance to the line of force. You take that force line, you extend it as far as you need to find the point where it's perpendicular.
So when you're solving problems like this, you just have to be conscientious of that, because we put the point to be at the base of the ladder, that it's going to be whatever is perpendicular to it, the force perpendicular to it.
Okay, being general in answering your question, you always need to identify where you're going to sum the torques first. And you want to choose that place judiciously, like we did here. We chose the base because it would make 2 of our forces give 0 torque. And then after you've made that judicious choice, then you need to find what the perpendicular distance from the place you're summing to the line of force for each force is. And then determine the direction of the torque, whether it's positive or negative, which I forgot to do the first time through. We had to come back and do it after I'd written down the magnitudes. Need to do both of those.
Okay.
Any other questions about the problem? All right. Now to a new problem, one that uses a simple machine. Now, simple machines is defined 2 slides below this. But a simple machine is a device that has as its goal to allow us to do work by putting in less force. It is not something that produces work. We don't put in some work and it does more work. That's not possible. That's a violation of the first law of thermodynamics. But we can ideally put in work and have the machine do the same amount of work that we did. But remember, work is force times distance. So the force times distance in should equal the force times distance out if we have a perfect machine. How could the forces be different? Well, let's have an example. This right here. I don't know if you thought I was doing anything special. So I was setting up a type of simple machine here. This is a lever. Now right now it's balanced. What does it mean to say it's balanced? Well, it's in equilibrium, which means the net torque is 0. If I put a mass of 500 grams on here, so I'm going to put a mass of 500 grams, I'm going to put it there. Can I hold that? Okay. I'm going to have to put it in closer. Okay, put it there. Can I hold that up with this mass of this mass of 200 grams? Can 200 grams hold up 500 grams? Depending on where I place it. If I place it out here, it actually is lifting it. And so I can bring it in until I get it balanced. And it's hard to get it just right. Getting close. Too far. Seriously. I had it here and it was too far one way. There we go. Have it balanced. Since it's balanced, what condition do you know is true? It's in equilibrium, which means some of the torques is 0. Now we also have some of the forces is 0. If you look at the forces acting on that meter stick, you have the force normal that's pushing up at this point. You have the force of gravity here pushing down, force of gravity here pushing down. The other condition, sum of the torques is 0. Where should I sum the torques about? Okay. James says the fulcrum. The fulcrum is the balance point here, the place where I have something pushing up. The reason we typically choose the fulcrum is because that way we don't have to calculate what the force the fulcrum is supplying is. We could have summed it anywhere, but we would have had to find out what the force from the fulcrum is if we chose a different place. So that's why we choose the fulcrum. So summing the torques, this one here is a distance of 1, 2, 3, about 4 inches away from the fulcrum. This one here is a distance of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a little over 11 inches away from the fulcrum. So if we calculate the torques, we would have about 4 times 0.5 kilograms times G. That is a positive torque. This one here, about 11.5 times 200 or 0.2 kilograms times G, and that is a negative torque. Those should add up to 0 if it's truly balanced. Now, of course, I told you my measurements are pretty rough here. So I'm sure my numbers didn't come out right. That's because of the rough measurements. So this is an example of a simple machine. I put in 0.2 times 9.8, which is 1.96 newtons. And it's able to hold up 500 times 9.8 or 4.9 or 0.5 times 9.8 or 4.9 newtons. So a smaller weight holds up a bigger weight. How is this not going to violate anything? If this moves down some distance, this one moves up a much smaller distance. So the work done over here is going to be the distance this moves times this force. The work over here, the distance it moves times this force. Those two ideally are going to be equal. So that's what you have with a simple machine. You have something that's going to make it require less force to lift something, but you're going to have to move a lot more. The traditional simple machine, you have something heavy down here in the end, You put the fulcrum, okay, so like this, and of course I'm going to tip it with this system. But I put my force out here, and the force I have to apply is far less than the force that I'm putting on that mass. But I moved this a distance of about half a meter, and this moved up only about 10 centimeters. So the distance this moved is far less than the distance this moved. So the work I did is my force times the total distance I moved. The work done on this is its weight times the distance it moved. Those will be equal, but my force is much smaller. My first experience with this was like this picture. Back when I was 14, I think, my dad got this bright idea of buying this beat-up Toyota Corona that didn't run. And so we bring it home. He's all, now, all you have to do is fix it. And so he brings in a little engine puller thing, and I've got a block and tackle system, and I put the chains on the engine, take off the bolts, and I start pulling on this thinking there's no way I'm going to lift it up. And I'm like, I totally was very easily lifting the engine out of the car. Wasn't all burly. I was easily lifting it because the pulley is another example of a simple machine. It gives you what we call a mechanical advantage. It multiplies my force. But one thing I noticed is I had to pull that chain like 50 feet to raise the engine like 2 feet. And of course, I didn't know what was going on. I hadn't taken any physics yet at this point. But the reason I had to pull the chain so far was so my work was equal to the work done to lift that engine 2 feet. So my force was really small compared to the weight of the engine, but the distance I had to move was really large. Now this here is a simple example of a pulley system. We have a pulley down the bottom, and it has a load attached to it here. And we have a string with tension T that is wrapping around it. For the purposes of general physics, we will assume that those strings are perfectly vertical. Obviously, the picture does not show that it's perfectly vertical, but we'll assume that they're perfectly vertical. If those strings are perfectly vertical, then each rope is applying a force to the pulley. How big is the force each rope or string is applying to the pulley? The definitional thing. 2T. Well, each rope is T, so the total is 2T. Because the rule is, if you have a cable, it applies a force equal to the tension in the direction that the cable is leaving, any place it leaves. So we have the cable leaving two places, and each place is putting an upward force of T. So we have 2T pulling up. So now we can right away say, how much force do I have to apply here to raise, let's say this has a weight of 100 newtons. How much force am I going to have to apply there to lift 100 newtons? How hard am I going to have to pull the rope to raise 100 newtons? Right, it's going to be 50 newtons because following what DJ said, we have an upward force of 2T, 2 times whatever force I'm putting on that rope. So if I need to pull up something that's 100 newtons, I just need to pull it 50 newtons, 1/2 of that, to lift it. So we say this gives me a mechanical advantage of 2 because the force that's going to apply to my load is 2 times the force that I put in. And you notice they put the free body diagram here because you put sum of the forces in the y direction is equal to MAY. We assume that you're lifting it at 0 acceleration. That is, you're just moving it at constant speed. And so you get 2T minus weight equals 0. 2T equals weight. Tension is equal to weight divided by 2. So this asks the first question, what would be, very awkward phrasing, what would be the tension in the rope in newtons? Well, if the engine was 117.5 kilograms, I'm just laughing because any real engine, we're probably not strong enough to just have a 2-to-1 ratio and lift it. 117.5 kilograms, what's the weight of 117.5 kilograms? Yeah. 117.5 kilograms times the acceleration of gravity. Here's how I can make it fit. And so that's the tension. It was a simple calculation. Anytime you have a pulley system, it's fairly simple. All you have to do is take the pulley where your mass is connected to and count how many times the string is going up. If it's a simple pulley system like this, the tension is the same in all the strings. Remember, I already identified the ideal conditions. Ideal conditions, the pulleys have no friction to rotation. The strings have no mass and don't stretch. We'll even go so far as to say the pulleys don't have any mass. Obviously, we don't make any pulleys that fit this definition, but that makes our calculation simpler. Wow, I have 4 minutes left. If you look at this picture, it has a part B. How much force is pulling down on the ceiling?
It's just the weight.
It's not just the weight, because I'm also pulling down on the rope. Now, this picture shows me pulling at an angle of about 45 degrees. If it was an angle of 45 degrees, I would have to take the vertical part of that, the vertical component of that, plus, of course, you have those 2 tensions pulling down to get the total. Once again, for the purposes of general physics, we assume that you're actually pulling straight down. And so you would have 3 tensions pulling down, so the ceiling would have to hold up 3 tensions. But in real life, you very well could be off to the side pulling like this. So we want to simplify for physics purposes. Why? Because we don't want to make the problems harder than they have to be. We want you to understand the basic concepts. And so I'm going to stop with this. Back when I was in high school, I worked at the dairy. And when they were chopping the corn, me as a little pipsqueak freshman, my job was to change tires every time they popped a tire, which was approximately once an hour. And so they bring in these tires, and you have to take them off of the feed wagon. And those things were rusted in place. And so here I am, believe it or not, I was like 130 pounds as a freshman in high school. And I'm trying to take those off. And I had a real problem. I just did not have the strength lifting up. I could jump onto the breaker bar as many times as I wanted, it wouldn't come off. But there in the shop, we had a 6-foot stretch of pipe. You put the 6-foot stretch of pipe on your breaker bar, and voila, it comes off. Either that or you can break your socket. Why was little pipsqueak Richard able to get the nuts loose using that 6-foot cheater bar? I increased the lever arm, and torque is R cross F. You increase the R, you increase the torque. And so that is another example of a simple machine, just increasing the angle or the lever arm. You have a simple machine. I will stop here instead of trying to get into the ramp and stopping 2 seconds into the ramp. So have a great long weekend.
So, for that problem that you solved,